The Internet routes billions of queries a second to translate domain names, synchronize global clocks, and stream real-time video. These services, DNS, DHCP, NTP, and WebRTC, constitute the underlying infrastructure of the modern web. Yet all of these systems rely on a single transport mechanism codified in August 1980, RFC 768. It is a protocol that mathematically guarantees absolutely nothing about the delivery, ordering, or successful arrival of your data. This is an intentional design choice. The early architects of the Internet operated on the end-to-end principle. They determined that complex functions, like error checking and sequence tracking, should be handled by the computers at the edges of the network, rather than forcing the core routing hardware to manage communication states. The User Datagram Protocol, or UDP, actively strips away the connection handshakes, sequence tracking, and flow control mechanisms found in its counterpart, TCP. It fires discrete datagrams into the network and immediately forgets them. By explicitly omitting these management features, UDP achieves maximum theoretical throughput and zero connection setup delay. But that exact same statelessness creates severe cybersecurity vulnerabilities, allowing malicious actors to weaponize the protocol's lack of validation. Because TCP's rigid state management creates inherent latency, the modern Internet is increasingly building complex, stateful features directly on top of UDP. This allows developers to combine raw transport speed with their own customized security and reliability layers. 40 years after its creation, UDP's continued dominance proves a counterintuitive reality. A raw, unmanaged datagram interface remains the essential foundation for high-performance network engineering. When an Internet Protocol, or IP, packet arrives at a machine, it only knows the destination hardware. The operating system needs a Layer 4 transport wrapper to demultiplex that data and route it to a specific application, like a web browser or a game client. TCP accomplishes this with a heavy header, requiring anywhere from 20 to 60 bytes of overhead. UDP, conversely, achieves application routing using a hyper-efficient, strictly fixed 8-byte block divided into just 4 fields. The first two 16-bit fields are the source port and the destination port. They tell the receiving kernel exactly which application should process the incoming data and where to send any potential reply. The remaining fields are equally sparse. The length field defines the total size of the datagram, and the checksum provides a mathematical mechanism for basic error detection. UDP calculates this checksum using its own header and payload, while also conceptually prefixing a 12-byte pseudo header directly from the IPv4 layer before running the final calculation. This pseudo header includes the source and destination IP addresses. By merging these into the checksum, the UDP module verifies that the transport unit actually reached the correct recipient and wasn't accidentally misrouted by a corrupted IP header along the way. That length field technically supports datagrams up to 65,535 bytes, but physical network architecture imposes a strict limit. Standard Ethernet hardware uses a maximum transmission unit, or MTU, of exactly 1,500 bytes. If a developer sends a UDP message larger than this MTU, the IP layer must fragment the datagram into multiple smaller packets. Because UDP has no mechanism to request the retransmission of individual fragments, if a single piece is lost in transit, the receiving kernel drops the entire original message. Without error recovery, network engineers have only one practical option. They must mathematically size their application payloads to perfectly fit within that 1,500-byte boundary, ensuring clean transmission across the physical wire. This strict, minimalist architecture enables massive horizontal scaling, particularly for the Domain Name System, or DNS. This timeline shows the difference in execution latency. A TCP connection requires a 3-way handshake, costing a full round-trip time before any data is sent. DNS over UDP executes a complete query and response in exactly 1 round-trip time. Authoritative DNS servers handle millions of concurrent queries. If they had to maintain a continuous TCP state for every single user, they would instantly exhaust their available memory and CPU. UDP allows the server to process an incoming query, dispatch the single packet response, and instantly wipe the transaction from memory. This stateless design is also a functional requirement for local network configuration. When a new device boots up, it doesn't have an IP address, and it doesn't know the address of the local DHCP server. TCP is a strict point-to-point protocol. It cannot execute its handshake without two previously established IP addresses. UDP natively supports broadcast messaging. The new client simply sends a datagram addressed to the entire subnet at once, allowing the hidden DHCP server to hear the request and initiate the address assignment. High-throughput user applications like VoIP, Zoom, and live video streaming also rely on UDP, but to solve an entirely different bottleneck.
In a continuous media stream, TCP suffers from a critical failure point known as head-of-line blocking. If a single TCP packet is dropped due to network congestion, the protocol completely halts the application stream. It refuses to deliver any subsequent, perfectly valid packets until the missing data is successfully retransmitted, causing the video call to freeze. UDP operates on an anti-stall philosophy. It passes every received packet to the application immediately. If a packet is lost, the video codec accepts a momentary visual glitch in one frame rather than stalling the entire stream. This diagram shows how applications handle variable network latency using dynamic jitter buffers. The buffer intentionally delays irregular incoming packets by a few milliseconds, releasing them at a perfectly smooth, constant interval to mask the network's instability. For real-time communication, strict timeliness matters more than total accuracy. UDP's fluid delivery architecture sacrifices a few dropped frames to maintain the forward momentum of the stream. Operating a transport protocol entirely without connection handshakes introduces severe cybersecurity consequences. Because there is no initial validation, an attacker can falsify the source IP address on an outgoing UDP datagram, a technique called IP spoofing. The attacker sends this spoofed packet to a high-bandwidth server. The server assumes the request is legitimate and blindly trusts the source IP. It acts as a reflector, sending its response data directly to the attacker's intended victim. This chart displays the bandwidth amplification factor of various protocols. It measures the exact ratio between the size of the attacker's initial request and the size of the server's reflected response. The Memcached protocol demonstrates the catastrophic limit of this vulnerability. A 15-byte spoofed request can trigger a 750 kilobyte response. That is a 50,000 times multiplier effect directed entirely at a target's infrastructure. The exact stateless efficiency required to run DNS and NTP is what weaponizes those same servers. To mitigate this, internet service providers must manually implement source address validation at their routers, dropping outgoing packets with falsified IPs before they ever reach the open internet. Beyond malicious attacks, UDP's lack of state creates a functional roadblock for legitimate peer-to-peer applications operating behind modern stateful firewalls. Network Address Translation, or NAT, relies on connection state to route traffic. Because UDP has no handshake, the firewall has no way to verify if an incoming packet is a legitimate response or unsolicited data, so it defaults to dropping the traffic. To bypass this, developers utilize a framework called STUN, Session Traversal Utilities for NAT. A local device sends a request to an external STUN server on the open internet. The STUN server inspects the packet and replies, effectively telling the local device its own public IP address and the specific port the NAT router opened for it. The device can then share these public coordinates with a peer to attempt a direct connection. Operating a stateless protocol within a highly secured, stateful network perimeter forces software engineers to build complex traversal workarounds just to establish basic host-to-host connectivity. Modern applications require integrated encryption and reliability, driving a new evolution in transport network architecture. Standard UDP relies on an all-or-nothing checksum. If a single bit flips in a 1500-byte video frame during transmission, the receiver's kernel discards the entire packet. RxC 3828 introduced UDP Lite to address this. It implements partial checksum coverage, protecting critical metadata headers but leaving the actual payload unprotected. This allows error-tolerant video codecs to process slightly corrupted payloads rather than dropping the frame entirely. But the most significant shift in transport architecture is the QUIC protocol, formalized in RFC 9000. This diagram shows QUIC operating within the application space. It uses UDP as a raw, underlying datagram bedrock,
but builds multiplexing, congestion control, and TLS 1.3 encryption directly on top of it. Because the transport and encryption handshakes are combined, QUIC achieves a zero RTT connection for returning clients. A website can start sending encrypted data in the very first packet, eliminating the 300 millisecond delay inherent in traditional TCP setups. To solve UDP's security liabilities, QUIC enforces a strict anti-amplification mandate. A server will never send more than 3 times the data it received until the client's IP address is definitively verified. Traditional UDP will remain the tool of choice for simple infrastructure queries. But the bulk of global web traffic is transitioning to QUIC. By wrapping complex state and security around a stateless core, QUIC proves that a raw, unmanaged datagram interface is the foundation for the modern internet.